My name is Richard Freund. I'm CEO of Konker, as Charles already introduced me. And we do work with cosmic rays to bring safety and sustainability to, especially to the mining industry. So let's go through the presentation. First of all, 5 seconds about Konker, who we are, what we do, and where we come from. So we are a mining startup company, as I said already. We are a very proud member of the MICA network. We're very happy to be part of it. And we started 6 years ago as an IoT platform, and we migrated towards the mining industry. We still use our IoT solutions, as I will tell you later on. We use the power of nature to solve human problems. We like that slogan. I think it's very rich in this time of life as we are of humankind, because we need to go back to the nature to solve nature in a way. And we have corporations in Canada and in Brazil. So that said, what are we seeking here today, or what are we looking for? Is one is, of course, mining companies to increase their safety and productivity with our products. But however, we also are looking for consulting companies that can or see a possible accelerator with our konker solutions. Third is if there's any mining providers that are planning to expand to Brazil or to Latin America, we are very happy to talk about joint ventures. And then again, there's the science part, where we do want to research every time more about muons and how they work, and all that science that goes with it, and how we can bring that to an industrial standard level of solutions. So that is about us, about konker, about what I expect from this presentation today. Let's go a little bit quickly through to tailings. What on earth is tailings? What do we consider tailings? So first of all, you have, like in the mining industry, you get the ore from the rocks. You get the rocks, then you grind them, then you separate the good from the bad. You separate the ore from the rest, and the rest that's not important for the ore process, you put water to it, and then you put it in tailings ponds and tailings pits. So this is what is called the tailings, or what we consider tailings. So it's leftover material from a mining process, byproduct, and consists of a slurry of fine particles. It's not very sympathetic. It's it has like sand and micrometers. It has small particles in it, and people say it's sometimes it's toxic, sometimes it's not. It's not very sympathetic, as I said. So that's tailings. And where do they stay? What where do mining companies keep them? In tailings dams. So here you have a tailings dam, and here's the tailings inside, which is like the lake here, and right next to it you have a little village. So why is it important to keep these dams safe, or monitor them? Because if they are not safe, then obviously they generate a huge risk for population and for society and for the environment and for everything. So they have to be as well stored as possible, these dams with the tailings, as I've said before. So what is it? They're embankments designed to permanently store the tailings, so that's very important. They're uniquely tailored to the environment where they have to fit in. They're highly engineered structures, and tailings storage facilities, TSFs, are one or more tailings dams that you can consider. So they're highly engineered, yes. However, every now and then we do have a tailings breach, or a tailings was a tailings dams breach in Brumadinho in Brazil, which was a disaster that took the life of 270 people. So that is not good, of course. And then there's a lot of tailings storage facilities globally, worldwide. So we have to see how we can keep them safe. So there's data that shows that a third of the world's tailings dams are in high risk, with catastrophic damages to nearby communities if they crumble. So that's, of course, something that we have to avoid at all costs. There's another prediction that 13 catastrophic failures will happen between 25 and 29. And there's a potential liability, which I suppose it's much higher than this that they're saying here. So what we have is, we have almost 700 tailings dams that are classified as high-risk tailings dams. Where are they? They are in Canada. More than 250 are in Canada, 217 are in Brazil, almost 300 in Australia. Then you have around 200 in South Africa and in the United States. These are the amount of tailings dams in itself. The amount of tailings dams that are of high risk is the ones that are in green. that are the high risk ones here. They're either active or inactive. However, they are in high risk of being a threat to people living nearby. So that's an issue, that is a problem that we want to address. And of course, not just us. There's like lots of many regulamentations and institutions and associations that are working in favor of not having any other tailings dams catastrophe again. So you have the Mining Association of Canada, Mining Watch, the Responsible Mining Foundation. Here you have the global industry standard of tailings management. Here you have the Sustainable Development Goals towards sustainable mining, and all is supported by the United Nations Environmental Program. So going quickly through these regulamentations and companies that work with them. So International Council of Mining and Metal is a company that's been around for more than 20 years, that is working on standards so that if everybody follows these standards, if every mining industry is able to apply the standards set, mining will be much safer and tailings dams will not break or not break that off, not break, which is of course the main goal. Here we have another Global Tailings Management Institute, which is a conjunction with the United Nations Environment Board, the Church of England, and the global industry. They created the Global Industry Standard of Tailings Management, which is this one, which then again has also the International Council of Mining Metal to it. So there is like a community, and this is not by far not a complete list. There's a community of institutions that work to get tailings safer. The Sustainable Development Goals as well, which are based by the United Nations, which are good for not just for tailing, but for a better life in itself. In Canada, we have the Towards Sustainable Mining, so from the Mining Association, which is again a framework and protocols for safer measurements and for safer minings. How do you monitor tailings dams today? So what is happening today if we have all these regulations, and so how do we try to keep them in place? You have a couple of technologies that I want to go quickly through. One is a radar. So you have like a radar that you fly with a drone over wherever you need to monitor. The other thing is a light detection LIDAR, which is like something like this, where you have a laser scanning the environment the entire time. You have seismic sensors, which is, it's not a good picture here, but they're here in the tailings dams. There's seismic sensors. They're sending their signals up to somebody who's listening to them, to be it a satellite or some other gateway or something, to communication, and they will alert as soon as there's some seismic change within the tailings dams. There's a simulation from outer space with satellites as well, which is the INSAR satellites. They all have their benefits. There's another total like a similar to the LIDAR. It's another technology, but it's, and again, it's with lasers. It's being measured with lasers, and it's quite accurate actually. And then you have the security operations centers, where you get all the information together and you stay monitoring. You start monitoring the entire all the systems, and to make sure that you find out as soon as possible that there's anything that has to be avoided to happen. Us, konker, how do we approach the situation? We do work with the cosmic rays, which I will start talking about in a second. And our approach is to not just look at the dam in itself, but also at the dense stuff within the tailings dam. So it's not just the dam, but it's also the mud, the stuff that's in the water there. So we created a Muon-Telescope, which is a autonomous and self-calibrating, so you can just deploy it and leave it there happening, getting the information. It develops 3D models, and it has a dashboard where you can get the data from. It has a communication gateway that runs on our own IoT platform, and it's a robust and low-cost solution. So it's something that we managed to produce in a price range, which I suppose is different from the price ranges that you usually see with these kind of solutions and situations. We managed also to create our own scintillator, so we do supply our own tech stuff for the telescope. Well, actually, the scintillators are just being rolled out, so just to be correct about that, but that's going to happen in the very near future. So what are muons? Muons are particles, electric particles like electrons, and they are raining on the Earth the entire time, 24/7, all day long and all the time. And whilst they get on Earth, they penetrate through any matter, through any material, that's in their way, or that they walk through, that they penetrate through. And while they get through these materials and they penetrate deep into the earth actually as well, their attenuation changes. So the characteristics that they carry change, the way they fly change, the attributes, how they behave change. So once we capture the muons after they went through something, then we can find out what they went through, which I'm going to try to explain you in really quickly here. So what we have, it's basically like an X-ray tomography. So in X-ray, you have an object, in this case, it's a cow, then you put the X-ray to it, you throw the particles at her, you take the picture of the cow, and you have the X-ray of the cow. With muography, you have the entire shower. You don't have to put any X-ray machine to nobody, because the showers are happening all the time. So the muons are raining on the earth. So you have the cow, and everybody is already exposed to muon. So you have the cow here. You put our telescope under, and the cow here is just an example, because it wouldn't work with the cow. It has to be bigger and it has to move less. But with the cow, so you put like the telescope underneath the object that you want to monitor, that you want to measure. Then you capture all the muons that are coming, that travel through the object. And then what we do is we analyze the information that we capture with our telescope, and we are able to generate a 3D image of whatever we were wondering, we were monitoring. So that's how muography works, basically, in 5 minutes. So what is driving us? Why do we want to work with this? Because we are convinced, as I said already, that nature provides solutions for solving human problems, and we understand ourselves powered by nature, and we are sustainable, secure and predictable. We deliver these stuff with the predictabilities in favor of life. We want these stuff, the catastrophes, not to happen anymore. We do make the hidden visible without digging, drilling, or probing, or so without any going to the dam and trying to get some seismic information, stuff like that. We just get that through the rays. So we do capture and interpret the muon-rays, and with large volumes, because they only work with large stuff more than 10 meters high that doesn't move too much, or that doesn't have too much of an inertia to itself. So with that, we measure the density. The humidity is something that I will talk about. It's not going with the muons. It's going to happen with neutrons, but we do that too. We measure density, weight, volume, geometry, and purity of dams. And we also apply it to ore piles, pits, and other objects in the mining industry that stand almost still, that don't move too much. So we do, as I said already, we have developed our cosmic telescope, which is innovative to the current methods. However, it's been around for a while, this technology, but we managed to get it with the self-calibration to a new level. We do measure the density, as I said already, and that's very, very ESG-like, very green, as I said. So here's the humidity. We do measure humidity with neutrons. So we use our same telescope, and where we measure where we capture the neutron, the muons, we also have the same technology to capture neutrons. With that, we can measure the humidity of whatever particle or whatever object we're measuring. We do have a patent running for our technology. So our data can be consulted in real time via dashboard, which is of course state of the art. So going to the tailings dams. How do we do that, or how does it work, or what does it do? So the safety and predictability of tailings dam stability by measuring dam density with Muon-Telescope, possible point of weakness by analyzing density changes in dams. So how does that go? We put a couple of telescopes on the base of the dam, and with capturing the rays, we can tell you, we do a 3D reconstruction of the dams, and depending on how many telescopes we have and how the geological conditions are here down at the dam, we can give you results in quite a short amount of time. So we have the first results within a couple of weeks, if you want. So here is why we believe that our solution is one of the differences, or one of the charms of our solution, we understand, is when you have a tailings dam, you have the dam right here. This is what you see. So you have all your sensors in the dam and everything, and maybe even somewhere here. But what we do is we get, when we put our telescope down here, we get this. So we are capturing almost 180 degrees from muons, which are around. So when they come this way, we have a clearer picture. When they come from the side, we have a not so clear picture, but we still have information about that. So we know what's happening here, because over time here in this tailing slimes, as it says here, the things get messy. So some dense stuff was put here, and then it floats over here, or it wasn't supposed to be here because there's a layer of 20 years ago that nobody knows about, and under the layer there was a pocket of some other material that may not hold sustain the weight, and so all this stuff we can measure with our we get the information with our telescope, with our technology. So that's why we think it's relevant. So then we have a couple of benefits. We do measure the mass with high accuracy. We have the inference of density, which I said. We get the inconsistencies of other conspicuous marks, and we integrate with the plant's monitoring system. Of course, we get the information to the whole process. We operate constantly independent of weather conditions, so it's 24/7, so you don't have to fly a drone or anything. And we keep the data for retroactive analysis and seasonal project, is of course the state of the art as well. So that is our Muon-Telescope for tailings dams. We do also apply the technology for other specificities in the mining industry. So what we do, for instance, is we monitor ore piles. So with ore piles, the problem or the situation, of course, is not so security prone. It's different. We want to know, or the mining companies want to know, how much is in their piles, because the piles, they change all the time. So we measure them, and also how pure they are. So we can validate the quality of the ore whilst on the pile. We have the 3D mapping, and with that we integrate we have the lean decision making, so you can decide the sooner the better how good or how well your pile is, what's the quality of your ore, right? So here's a little bit of how it works. We put 1 or 2 telescopes underneath the pile. We put it through the same data processing on the same platform, and we integrate with the same systems. We have pretty much the same benefits. Also, it's 24/7. The difference here is that you have also the differences ore and density and quality. So you have the quality of the ore whilst it's on the pile. You can already decide that, and that and impurities and contaminants we can already just tell when it's on the pile before it gets into the process of steel making. Another application is pit densities. I'm going to pull towards the slide further on. So what we have here is a pit, the ones that we were monitoring the dam before. What we do also monitor the sedimentation within the pit. So we put a tube, like a 30-centimeter tube, into we submerge it into the pit. We lower down a couple of telescopes. So here 3, but it's going to be more in time, and they capture all the rays around here, and with that they measure the density of the sedimentation part, so that there is no risk to any breakage or anything. And also the pit is going to be used the most efficient way possible, because we know how much sedimentation there is and how strong it is. So then you know how much you can still, how much waste you can still put to that pit until it's saturated, so to say. One last measurement that we do also is in thickeners. So what we do is we put under thickeners, we measure, put the telescopes, because in thickeners you have to avoid stains in the maintenance, because you cannot look inside them. So you have also the need to know what's going to happen in there and stuff like that. So we have that solution that can help you to adjust the operating parameters according to the exact density that you find inside the thickeners. This is the telescope in itself. So the assembly time in inside takes 1 to 3 months. The smaller telescopes are 30 centimeters. The taller ones are like a little fridge. The power supply is normal. They need a Wi-Fi internet connection. The angle of how they capture the rays is 180 degrees. The rate that they're working on is 10 hertz. We can increase that on necessity, but the way they're designed now is 10 hertz, so that they also don't consume too much energy. They work in any kind of weather condition. They work internally, externally submerged, and they are autonomous, as I said, and self-calibrating, so that you can just keep them wherever you deploy them, and the maintenance is very, very, very low. So to resume that, what applications in mind? So we have the tailings dams, where we have the validation of the safety measurement and density to avoid the failures. We have the applicability for the ore piles, where we measure mass and quality in real time. So you're getting control and you can take better decisions. In ponds, where you measure density of the sedimentation layer to keep the ponds sustainable, the use of them. And then the thickeners, again, that we measure the density inside, so you know what's going on in there. So the general benefits is to make tailings safer, to protect communities, to make mining more efficient, to reduce greenhouse gas emission, carbon footprint, and water. It's cost efficient and ROI-based in its pricing, so it's a cost-efficient telescope, it's a cost-efficient solution. We use, again, the power of nature, which are the muons, for the benefit of mankind. Two customers that we have today is Anglo American and Samarco. They are using our solutions. I'm happy to go into more detail for that if we have some time left. This is the team that we have. So we have a couple of PhDs based in Brazil. One external, first guy from Cambridge, and me, I'm from Germany. Other stuff that I'm passionate about, just quickly going about it. So I do like to play the drums, to sing. I like to sing. I don't know if anybody likes to listen to me, but I like to sing. I like to ride the bike, the motorbike, and do some water sports. And I'm married. I'm happily married. I forgot that. Sorry. So here's a little bit of information that was released in the press. So about in the Canadian Mining Journal, and the stuff about Anglo American the projects. So what would we need to know from you if we would go into a project? We need to know the size of the dam or the object that's at stake, the time frame for the information, so how fast you need to have the information, how high the resolution has to be of what you're looking at, so how high res or low res it has to be, the physical structure of the environment, so to see where we can deploy our telescopes, how that can be. Then that will result in the quantity of telescopes and the time, the assembly time between the 1 and 3 months that I told you, the installation, and then the monthly fee that the solution is gonna cost or take. And it's easy to install, so that's important too. So there's no like a huge project for installment or for anything like that. And that was it. So that was what I had to share with you today. Charles, you wanna?
Yes. Thank you very much, Richard. Richard, what I'm going to ask you to do is read the questions in the chat box and read them out loud, and then answer the question. And then when you're done reading the questions in the chat box, I'll come around with some additional questions that I've also come up with. But please go ahead and read the question in the chat box and answer the question. But please make sure you read it out loud so that everybody can hear the question.
Sure. Oh, how many telescopes are needed per acre of tailings storage facility? It depends on how high the dams are, and it depends on how the storage facility is. But usually it's about a telescope every 60 meters, something like that, 50, 60 meters. Prosper. Okay. Mark. We do have Mark.
Richard, if you can just read the question out loud so that everybody can hear it.
Oh, I'm sorry. Oh,
no problem.
Yeah. So the first one was how many telescopes I needed. I don't remember if I said that. The second one was so long that I started reading and I forgot. The commercial muon detector that I am familiar with, Mark is saying that, Mark told you. The commercial muon detectors that I'm familiar with require sampling for weeks or months at a time. How do you reconcile this with such a dynamic environment as a tailings dam, where much shorter terms information is needed? So what we do is we calibrate our telescopes up front. For that takes a while, but once they're in place, we have, and that also again depends on the size and on the layout of the structure where we deploy the telescopes. But once we have that, we get the information in a much shorter time range. So that should be working. But we can go deeper into that if you have some technical issues or questions, and I'm more than happy to discuss that with you. The dimensions, Mark, I think I talked about this already. What the dynamic dimensions of the telescope. Andre Perio, can this be used to characterize loss of contaminant film permeability due to filling of interparticle voids by precipitation from acid rock drainage? I'm not sure. I have to ask the tech guys to answer, because I don't want to say anything that that may be used against me afterwards. So Andrew, I'd be more than happy to answer that afterwards. We do have, Mark is asking how far out we are to be able to show some case studies. We do have case studies. We can talk about that, no problem. Stephen Goldman, I will reach out to connect on your solutions. Okay, perfect. Edward Thomas, a description of the Muon-Telescopes. It seems that the plastic scintillators you're using is also sensitive to neutron flux. Can your device reconstruct this? The direction of neutron flux as well? No, it's not. It's not this. It's not the same. Maybe I misspoke there, but it's two different scintillators, or two different technologies that are capturing, because neutrons are directed. So with neutrons, we have the issue that we have to really be underneath the object that we have to monitor, because muons, they come from all sides, but neutrons, no. So no, this is the answer to your question, Edward, is unfortunately no. Mark, can you elaborate on how are the telescopes deployed in the field? Are they on surface, at the toe of the embankment, or placed in ground? Are they robust enough to handle extreme climates? How does the Wi-Fi work? Is it omnidirectional? Does it require line side operation? So the Wi-Fi is omni. They are robust enough to handle extreme climates. However, we do have customers that they built a little hut where we put the telescopes inside. They can stand on they can be deployed on the surface. They can be deployed under the object. So we have, for instance, when we monitor the ore pile, we are underneath the ore pile. So there's a structure for that already. At some situations we ask to, and that's why I said we have to deploy first. We have to check out first how the environment is where we will deploy the telescopes, because sometimes we have to go, the further down we are and the closer we are, the better the image is. So that is the challenge, and that depends on the natural situation and on the landscape. Nicholas McDonald, in terms of monitoring ore piles, what is meant by quality and purity of ore piles? What data is being collected to define the ore pile from a geochemical standpoint? Does the quality of data captured change based on the metal it is being used for? So the quality, what I'm saying by quality and purity is the changes of density within the pile. So with that, we can validate what kind of material there is. So it's not 100% pure or exact, because it depends on the ranges of where we find that. But then again, we can go into that to answer that question in more detail if you want to, so that I will not, first of all, I will not talk longer than I have time, and then I will not say something that I'm not 100% sure of.
All right. Thank you so much, Richard, for those answers. And everybody who's on the call, we will be providing you a link to the recording of this webinar. And we are at the 2:30 p.m. now Eastern time, and it is the end of our call. So I want to thank again, Richard. Thank you to our guests for coming and taking the time. We appreciate you very much. Everybody, have a good day. We will see you later.
Thank you. Bye-bye.